At 1:55 in the morning on August 6th, the seafloor roughly 80 miles off the coast of southern Oregon lurched sideways. A magnitude 4. 9 earthquake tore through a stretch of oceanic crust known as the Blanco Fracture Zone, and 8 seconds later, 48 kilometers to the east, a second quake followed. Magnitude 4. 1. 2 ruptures, seconds apart, on the same fault system. Nobody on the Oregon coast felt a thing. No sirens went off. No tsunami warning was issued. And yet within hours, seismologists at the University of Washington, the University of Oregon, and the U.S. Geological Survey were pulling up real-time monitoring feeds, cross-checking waveform data, and asking the one question that always follows an offshore Pacific Northwest earthquake. Is this connected to the fault everyone actually worries about? Because 80 miles is not very far, and the fault everyone actually worries about, the one capable of producing a shock wave that could be felt from Vancouver Island to Northern California, followed by a wall of water tall enough to erase entire coastal towns, sits almost directly beneath where this new swarm was breaking. That fault is called the Cascadia Subduction Zone, and it has not ruptured in 326 years. This is the story of what actually happened off the Oregon coast this month, why scientists are watching it so closely, and why the fault that moved is, and is not, connected to the one that keeps emergency planners up at night. Start with the geography, because geography is the entire story here. The Pacific Northwest coastline sits on top of one of the most dangerous pieces of real estate on the planet. Offshore, the Juan de Fuca Plate, a relatively small oceanic plate, is being forced underneath the much larger North American plate at a rate of roughly 1.5 inches per year. That process is called subduction, and it is happening along a 600-mile arc that stretches from northern Vancouver Island down through Washington and Oregon to Cape Mendocino in Northern California. This is the Cascadia Subduction Zone, and unlike a normal fault where 2 plates grind past each other in small, frequent increments, subduction zones lock. The 2 plates catch on each other, pressure builds for centuries, and then, all at once, they let go. When Cascadia last let go, it produced one of the largest earthquakes in recorded history. The date was January 26, 1700, at around 9 in the evening local time. Modern geologists reconstructed the exact date using an unlikely source, Japanese written records. A tsunami with no accompanying local earthquake struck the coastal towns of Otsuchi and Kuwagasaki roughly 10 hours after the quake would have hit the Pacific Northwest, damaging homes, and in one town, triggering a fire that destroyed roughly 10% of the buildings. Japanese scholars at the time had no explanation for waves that arrived without warning. It took 3 centuries, and the science of dendrochronology, tree ring dating of drowned coastal forests, whole groves of trees killed instantly by sudden land subsidence, for researchers to work out that the orphan tsunami in Japan and a catastrophic quake in what is now Oregon and Washington were the same event. Estimated magnitude, somewhere between 8, 7, and 9. 2. For scale, that upper estimate puts it in the same range as the 2011 Tohoku earthquake that devastated Japan and triggered the Fukushima disaster. That's the anchor of this entire story, not the 4, 9 that just happened. That's the trigger for the conversation. The anchor is the fault sitting underneath it that has been quietly reloading for 3 centuries, and every time something rattles nearby, the question comes back, is this it? So what actually happened on August 6th? According to the U.S. Geological Survey, the 4.9 earthquake struck at a shallow depth. Reports place it in the range of 5 to 8 kilometers below the seafloor, roughly 128 kilometers west-southwest of Port Orford, Oregon, a small coastal town of about 1,100 people. Shallow earthquakes tend to be felt more sharply than deep ones because there's less rock between the rupture and the surface to absorb the energy. But at that distance offshore, in open ocean, there was nothing nearby to shake. A second quake, magnitude 4. 1 followed just 8 seconds later and about 48 kilometers away. Evidence that the initial rupture had triggered stress transfer along a nearby segment of fault, a common pattern in swarm-prone regions. Within the surrounding days, the U.S. Geological Survey's monitoring network picked up additional smaller tremors in the same stretch of ocean, part of a broader pattern of activity that has made this particular patch of seafloor one of the most seismically busy locations in North America over the past several years. The fault responsible is the Blanco Fracture Zone, sometimes called the Blanco Transform Fault. Geologically, it is a completely different animal from Cascadia. Where Cascadia is a subduction zone, one plate diving under another, capable of building up centuries of locked strain, Blanco is a transform fault, meaning the Pacific Plate and the Juan de Fuca Plate are sliding horizontally past each other. The same style of motion you'd find on California's San Andreas Fault, just underwater and far offshore. The zone stretches roughly 350 kilometers and includes a series of deep basins cut by parallel strike-slip faults, with a slip rate, the speed at which the 2 sides grind past one another, averaging around 2 centimeters a year. Its most active segment, the Blanco Ridge, is a roughly 150-kilometer-long right lateral fault responsible for most of the region's largest recorded shocks. Because it's a transform fault rather than a locked subduction interface, Blanco releases its stress in frequent moderate bursts rather than storing it for centuries. That's actually the mechanical reason it produces so many earthquakes. Instead of one catastrophic rupture every few hundred years, it lets go in increments over and over, magnitude 4s and 5s and the occasional 6, all the time. Records compiled by regional seismic networks show more than 50 notable quakes in and around Oregon's offshore waters over roughly the past 2 decades. And the Blanco Zone alone has produced clusters exceeding 50 individual earthquakes within a 24-hour span, including multiple events above magnitude 5. Here's where the story usually starts causing public alarm, and where scientists have spent the better part of a decade trying to calibrate the message. When a swarm like this hits, especially one large enough to make local news, people immediately think of the Cascadia Subduction Zone, because Cascadia is the fault with the giant number attached to it, magnitude 9, and the psychological gravity of the big one tends to swallow any nuance. Geophysicists who study the region have repeatedly and specifically pushed back on the idea that Blanco activity is a warning sign for Cascadia. Eric Fielding, a geophysicist affiliated with NASA's Jet Propulsion Laboratory, has explained that the Blanco Fracture Zone is not directly connected to the subduction zone, so it doesn't affect the fault underland. Harold Tobin, the director of the Pacific Northwest Seismic Network and Washington's state seismologist, has been even more direct, describing the Blanco Zone as a distinct and separate fault system from Cascadia, and characterizing the odds of it triggering a Cascadia rupture as close to impossible. So why does it matter at all if the two faults aren't directly linked? Because not directly linked is not the same thing as irrelevant. Both faults sit on the same tectonic boundary system. Both are shaped by the same regional stress field generated by the Juan de Fuca Plate's slow-motion collision with North America, and both are being watched by the same monitoring infrastructure. Meaning every Blanco earthquake is also functionally a live stress test of the sensor network that would have to catch the first seconds of an actual Cascadia rupture. Every swarm is data. Every data point refines the hazard models. And the hazard models for Cascadia are sobering enough on their own that scientists don't need Blanco to manufacture urgency. The numbers already do that. According to Oregon's Department of Emergency Management, current modeling puts the probability of a magnitude 7, one or larger Cascadia rupture, at roughly 37% within the next 50 years. That's not a probability of the big one specifically, a full margin rupture in the 8, 7 to 9. 2 range, but a broader threshold that includes both a full rupture and a partial one confined to, say, the southern or northern segment of the 600-mile fault. Even a partial rupture in the magnitude 8 to 8. 5 range would be catastrophic for the coastal Pacific Northwest. State planning documents estimate that in the event of a full Cascadia rupture, large parts of the region could be without basic services and outside assistance for a minimum of 2 weeks. And coastal areas could face a tsunami cresting as high as 100 feet in the most exposed, low-lying stretches of shoreline. To understand why the wave would be that severe, you have to understand what a subduction earthquake physically does to the seafloor, and this is where the science moves from abstract statistics into something almost tangible. When 2 plates are locked at a subduction interface, the overriding plate, in this case the edge of North America, gets pulled downward and compressed as the Juan de Fuca plate tries and fails to slide underneath it. Pressure accumulates for centuries. When the lock finally breaks, the overriding plate doesn't just shake, it springs back, snapping upward and seaward in a matter of seconds, sometimes by tens of feet. That sudden vertical displacement of an enormous slab of ocean floor is what displaces the water above it, and that displaced water is what becomes a tsunami. It's not the earthquake's shaking that generates the wave. It's the fact that a piece of the planet the size of a small country just moved. Detecting the earthquake itself is only half of that early warning chain. The other half is confirming within minutes whether a tsunami has actually been generated, and that job falls to a different piece of infrastructure entirely. The DART buoy network, short for Deep Ocean Assessment and Reporting of Tsunamis, jointly operated by the National Oceanic and Atmospheric Administration and its regional tsunami warning centers. These buoys sit anchored across the Pacific, tethered to pressure sensors, resting on the seafloor that can detect the passage of a tsunami wave, a change in water column height of just a centimeter or two, even in open ocean, long before that wave has built up into the towering surge it becomes when it finally reaches shallow coastal water. When an earthquake like the one on August 6th occurs, the National Tsunami Warning Center in Palmer, Alaska, automatically evaluates the quake's location, depth, and magnitude against a set of pre-calculated thresholds. A shallow offshore quake above a certain magnitude, typically in the mid-7 range or higher for this region, triggers heightened monitoring of the nearest DART buoys as a precaution, even before any wave has been confirmed. For the August quake, at magnitude 4, 9 The event never came close to that threshold, which is part of why no tsunami advisory was ever issued, and why the story stayed a regional curiosity rather than a coastal emergency. But the fact that the system is built to evaluate every offshore quake against that threshold, automatically, within moments of detection, is itself the point. It's the same infrastructure, running the same evaluation that would activate immediately if a genuine Cascadia rupture began. The historical record backing up all of this modeling doesn't just come from written accounts and Japanese tsunami records either. A large part of what scientists know about Cascadia's rupture history comes from something almost nobody outside seismology has heard of: turbidites, layers of disturbed sediment on the seafloor triggered when strong shaking causes underwater landslides along the continental slope, burying the ocean floor in a distinct layer of sediment that can be dated and matched across sites. By drilling sediment cores off the Oregon and Washington coast and counting these turbidite layers, researchers have reconstructed a rupture history stretching back roughly 10,000 years, identifying more than 40, likely full or partial, Cascadia ruptures over that span. An average recurrence interval of a few hundred years, though with enough variability in the record, sometimes just a century between events, sometimes closer to 1,000, that seismologists remain cautious about treating that average as a schedule. That caution is exactly why the field settled on a probabilistic figure like 37% over 50 years instead of a projected date. It's the honest way to communicate a hazard that is certain to eventually materialize but resistant to precise forecasting. Coastal Oregon communities within the tsunami inundation zone would have an estimated window of somewhere between 15 and 30 minutes between the shaking stopping and the first wave arriving, depending on their distance from the fault and local coastal topography. For towns built directly on low, flat river-mouth terrain, much of the Oregon coast fits that description. 15 minutes is not a generous window if evacuation routes are compromised by the earthquake itself, which is exactly the scenario. Emergency planners in the region have spent years trying to prepare for, through vertical evacuation structures, updated building codes, and public education campaigns. None of that is happening right now. That's the important distinction to hold on to. What happened on August 6th was a moderate, unfelt offshore transform fault earthquake of the kind the Blanco Zone produces on a fairly routine basis. Regional catalogs show comparable or larger Blanco events in June. In the days that preceded this one, and going back through 2026 alone, multiple magnitude 5 class quakes have struck the same general stretch of ocean. Scientists describe this as background seismicity, real, monitored, occasionally newsworthy, but statistically unremarkable in isolation. What makes any individual Blanco earthquake worth covering isn't the earthquake itself. It's the fact that it sits 80 to 150 miles from a fault capable of ending entire towns. And every time it moves, that proximity forces a fresh round of public reassurance that also happens to double as public education. A slightly uncomfortable but genuinely useful cycle where routine seismic noise becomes the occasion for reminding an entire region what's actually sleeping underneath it. There's also a quieter scientific debate buried inside all of this, and it's worth surfacing because it complicates the tidy narrative of nothing to see here. Seismologists have pushed back specifically on the word overdue when describing Cascadia. It sounds intuitive. The fault last ruptured in 1700. The interval between major Cascadia earthquakes averages several hundred years, based on the geologic and turbidite record preserved in offshore sediment layers. So the math seems to suggest we're somewhere in the danger window. But working seismologists resist that framing because earthquakes don't operate on a schedule. Paul Bowden, who has managed the Pacific Northwest Seismic Network, has pointed out that the underlying concept of a fault being overdue, as if it were a library book on a due date, isn't one that most seismologists actually accept, because the Earth's stress release cycle isn't regular enough to support that kind of prediction. The 37%, 50-year figure is a probabilistic estimate built from the historical rupture record, not a countdown clock. It means the risk is real and worth preparing for. It does not mean anyone can tell you which decade it happens in. That distinction matters for how you interpret every single offshore earthquake that makes headlines along this coast, including this one. A magnitude 4. 9 on Blanco is not evidence that the countdown has started, because there is no countdown to start. It's evidence that the plate boundary running along the Pacific Northwest is exactly as tectonically active as scientists already knew it to be, and that the monitoring systems built to catch a genuine Cascadia rupture are working exactly as designed, detecting, locating, and characterizing offshore seismicity within minutes, which is precisely the infrastructure that would need to function flawlessly if a real subduction rupture ever began. Zoom out from the fault mechanics for a second, because there's a human and economic layer to this story that rarely gets attention when the earthquake itself causes no damage. The Pacific Northwest coast isn't just scenic cliffs and small fishing towns, it's a working coastline. Ports at Coos Bay, Newport, and Astoria handle commercial fishing fleets, timber exports, and increasingly offshore wind development planning that depends heavily on stable seafloor geology assessments in these same waters. Every offshore earthquake swarm gets folded into the geological hazard surveys that inform where those future wind lease areas can safely be developed, because turbine foundations and subsea cabling both have to be engineered around fault proximity and expected ground motion. In a strange way, the routine hum of Blanco earthquakes is part of the baseline dataset shaping decisions about a multi-billion-dollar offshore energy build-out that's still in its early planning stages along this same stretch of coast. Small coastal towns like Port Orford and Gold Beach, the two communities closest to this month's epicenter, with populations in the low thousands, sit at the sharp end of all this planning. Both are built close to sea level, both depend on a limited number of road connections to reach higher ground, and both have spent years working with state emergency planners on tsunami evacuation routes, signage, and, in some cases, vertical evacuation structures, essentially elevated platforms or reinforced buildings designed to let residents get above an incoming wave when there isn't time to outrun it on foot. These aren't hypothetical exercises. Oregon's coastal school districts run tsunami evacuation drills the way Midwestern schools run tornado drills because, for a town like Port Orford, a real Cascadia rupture wouldn't arrive as a distant news story. It would arrive as ground shaking so severe that standing upright becomes difficult, followed by an evacuation window measured in single-digit minutes for the most exposed, low-lying blocks near the harbor. There's also the insurance and infrastructure layer, which tends to move slower than the news cycle, but is arguably where the real long-term consequences of Cascadia risk are already showing up. Oregon and Washington have spent the past several years updating building codes for critical infrastructure, hospitals, schools, bridges, specifically to meet Cascadia scenario seismic standards. Not because a rupture is imminent, but because the probabilistic hazard maps built from decades of research, much of it validated by exactly the kind of monitoring that catches events like this month's 4.9, keep confirming that the risk is high enough to justify the cost. Retrofitting Oregon's aging highway bridges alone for Cascadia-level shaking has been estimated in the billions of dollars, a bill the state has been chipping away at incrementally rather than all at once, in part because engineers can't fully rule out a rupture happening before the retrofit work is finished. So where does this leave the story of the August earthquake itself? In the most literal sense, it leaves it exactly where seismologists say it belongs. Filed as background seismicity on an active transform fault, logged into the U.S. Geological Survey catalog, cross-referenced against historical Blanco activity going back through 2026 and prior years, and used to fine-tune real-time detection thresholds. No damage, no injuries, no tsunami. No credible mechanical pathway by which this earthquake nudges the Cascadia interface any closer to failure, according to every geophysicist who has spoken publicly on events like it. The two faults are neighbors, not partners. One shakes constantly and rarely matters. The other has been silent for 326 years, and when it finally speaks again, will matter more than almost any other single geological event that could hit the west coast of the United States. But, and this is the part worth sitting with, rarely matters is doing a lot of quiet work in that sentence because it's precisely the reason scientists keep watching. Regional seismic networks don't get to decide in advance which earthquake is routine and which one is the first 90 seconds of something enormous. They only know after the fact, once the rupture has either stopped propagating or kept going. So every Blanco swarm gets the same treatment as a potential precursor until the data rules it out. Located, measured, checked against aftershock patterns, checked against strain data from onshore GPS stations that track the Pacific Northwest's slow, ongoing deformation as the locked Cascadia interface bends the coastline inland by a few millimeters a year. Deformation that, when it eventually releases, will snap back in the opposite direction all at once. That's the actual early warning infrastructure this region has built, piece by piece, largely funded and refined in the years since the 2011 Tohoku disaster forced a global reassessment of subduction zone risk. And it's the same infrastructure that responded to this month's quake within minutes. The open question, the one nobody, including the scientists closest to this fault, can currently answer, is not whether Cascadia will eventually rupture. The geologic record makes clear that it will. The only real ambiguity is timing, and possibly the extent of the rupture, whether it tears the full 600-mile margin at once the way the 1700 event apparently did, or breaks in smaller, still dangerous segments. What events, like the August 4th? 9 actually provide, beyond a brief local news cycle, is a recurring stress test of exactly how fast the detection systems respond, how well the public understands the difference between an earthquake happened near the dangerous fault and the dangerous fault moved, and how prepared the coastal communities sitting directly in the tsunami zone actually are for the 15 to 30-minute window they'd have if the next offshore rupture isn't a routine Blanco event, but the one everyone has spent 3 centuries waiting to not see coming. There's a technological layer to this story too, and it's arguably the most consequential thing that's actually changed in the years since the last major round of Cascadia panic. The West Coast now has a functioning earthquake early warning system called Shake Alert, operated by the U.S. Geological Survey in partnership with the Pacific Northwest Seismic Network and the Oregon Hazards Lab at the University of Oregon. It is not earthquake prediction. Nobody has cracked that problem, and most seismologists doubt it's solvable in any meaningful sense. What Shake Alert does instead is race the earthquake itself. When a fault ruptures, it generates two main types of seismic waves: a fast-moving, weaker P wave that arrives first, and a slower, much more destructive S wave that follows behind it. Shake Alert's network of hundreds of ground motion sensors across California, Oregon, and Washington is built to detect that initial P wave the instant it arrives, calculate the earthquake's location and likely magnitude in a matter of seconds, and fire off an alert to phones, apps, and automated infrastructure before the slower, damaging shaking actually gets there. For someone sitting near the epicenter, that gap might only be a second or two, not enough to do much. But for someone in Portland or Seattle, hundreds of kilometers from a Cascadia rupture point, that gap could stretch to tens of seconds. Enough time to drop, cover, and hold on, enough time for a surgeon to pause a procedure, enough time for automated systems to trigger, closing gas valves, opening firehouse doors, slowing trains before the ground starts moving beneath them. The system went fully live across all 3 West Coast states only a few years ago, with Washington completing the rollout in 2021, and it's specifically been engineered with Cascadia in mind, because a subduction rupture behaves differently from a typical crustal earthquake. A quake on a contained fault like California's Hayward Fault might rupture in a few seconds. A full-margin Cascadia rupture, tearing along hundreds of kilometers of locked plate boundary, could take minutes to fully unfold, which sounds terrifying, and is, but it also means the shaking itself propagates outward over a longer window, giving Shake Alert's sensor network more opportunities to detect it early and extend warning times to communities farther from the initial point of failure. Every Blanco earthquake that ripples through the monitoring network, including the one on August 6th, becomes another real-world data point feeding the calibration of that system, confirming detection speed, confirming that automated magnitude. Estimates track what independent analysts later confirming that the sensor network spanning 3 states functions as an integrated whole rather than 3 disconnected state-level systems. None of that technology, it's worth being clear, does anything to stop the earthquake or make Cascadia less likely to eventually rupture. What it changes is what happens in the seconds and minutes immediately after. And those seconds and minutes are, according to virtually every disaster planner working this problem, the entire difference between a regional tragedy and a regional catastrophe. There's also a persistent information problem that surfaces every time an offshore quake makes local headlines, and it's worth naming directly because it shapes how the public actually processes stories like this one. Whenever a Blanco earthquake trends locally, social media tends to fill in the gaps that scientific caution leaves open. A magnitude 5 shows up in a news alert, and within hours, unverified claims start circulating that the real magnitude was suppressed, that agencies are downplaying tsunami risk, that a swarm is a confirmed precursor to an imminent megathrust rupture. None of that has ever been substantiated by the actual seismic record. What tends to happen instead, almost every time, is that a scientist gets pulled into damage control, explaining, again, that Blanco and Cascadia are mechanically distinct fault systems, that swarms on a transform fault are not statistically linked to subduction zone triggering, and that the Cascadia hazard is real and worth preparing for on its own terms, without needing an unrelated earthquake 80 miles away to manufacture urgency. It's a strange information cycle, real seismic data, filtered through public anxiety about a genuinely catastrophic hazard, occasionally distorted into claims the data doesn't support, then corrected by the same small community of regional seismologists, who end up fielding the same question after nearly every moderate offshore earthquake. Pull back further, and there's a global comparison worth making, because Cascadia isn't a uniquely American problem. It's one entry in a small, grim category of subduction zones, capable of producing the largest earthquakes physics allows. The 2004's Sumatra-Andaman earthquake, magnitude 9. 1. Ruptured a subduction interface off Indonesia and generated a tsunami that killed roughly 230,000 people across a dozen countries, in part because the region lacked the kind of coordinated early warning infrastructure that exists on the U.S. West Coast today. The 2011 Tohoku earthquake off Japan, magnitude 9. 09. 1. Struck a country with some of the most sophisticated seismic monitoring on the planet and still resulted in roughly 18,000 deaths and a nuclear disaster at Fukushima, because the tsunami that followed exceeded the height that seawalls in the region had been engineered to handle. Both events reshaped how seismologists and emergency planners think about subduction zones worldwide, Cascadia included. Much of the current urgency behind Oregon and Washington's building code updates, tsunami evacuation infrastructure, and the accelerated rollout of shake alert traces directly back to the shock of watching Japan, a country far better prepared than the Pacific Northwest currently is, still absorb a death toll in the thousands. The uncomfortable lesson planners took from Tohoku wasn't that Cascadia would necessarily behave identically. It was that even the best prepared coastline in the world can still be overwhelmed by a subduction earthquake at the upper end of its plausible range, and that the Pacific Northwest, by most honest assessments, is not yet as prepared as Japan was in 2011. That comparison is also why the 37% in 50 years figure gets repeated so often in Oregon and Washington's own hazard communications, rather than buried in a technical report. It's a deliberately blunt number designed to sit in the front of people's minds the way a smoke detector's battery warning does. Not to predict a date, but to keep preparedness from becoming an abstraction. Emergency management officials in the region routinely pair that statistic with a second, more actionable one. The recommendation that households in the highest risk coastal zones be prepared to be self-sufficient for a minimum of 2 weeks, because in a full margin rupture scenario, that's roughly how long officials expect it could take before outside assistance reliably reaches the hardest hit and most isolated coastal communities, some of which would also have their access roads damaged or severed by the earthquake itself. For now, the fault that actually moved this month keeps doing what it has always done. Grinding, slipping, releasing its stress in small, frequent bursts that make headlines but rarely make history. The fault next door keeps doing what it has always done too. Nothing, visibly, while quietly building toward whatever comes next. Scientists will keep watching both, because right now, watching is the only tool anyone has. If you want to know what happens the day the quiet one finally breaks, that's a story with real consequences for millions of people along this coast. And it's one worth understanding before it's the one making headlines. What do you think the region's actual level of readiness looks like if that day arrives sooner than the models suggest? Let me know in the comments, and if this kind of deep dive into what's actually happening beneath our feet is useful to you, consider subscribing for more.